Hello, our paper title is Explaining Word Embeddings via Disentangled Representation. This work talks about introducing disentanglement into typical word embeddings to improve interpretability and flexibility. Here is the main idea. Given off-the-shelf word embeddings, such as pre-trained glove or what-to-vec, our goal is to find a transformation matrix which can transfer the given embeddings into a new type of representations. We call these new type representations disentangled word embeddings, or DWE. Our DWE can be regarded as a concatenation of multiple sets of subembedding. Ideally, information encoded in the original word embeddings will be extracted and separately encoded in different subembeddings. We expect that each subembedding set will be responsible for encoding a specific semantic or syntactic attribute, such as adjective, adverb, or semantics relevant to animal or location. To do so, our model requires some labeled data, such as a small dictionary indicating attributes of some words for learning the transformation. After learning, even if a word is not included in the label data, we can still transform its vector to get DWE. Also, it is possible that some attributes encoded in the original word embeddings are not in the attribute label set. In this case, information of these attributes will be encoded by the unseen subembedding set. Our DWE has three main properties. The first one is modularity. It means that an attribute should be encoded by only one subembedding set. In our methodology, we achieve this by optimizing mutual information. For example, let A be a random variable indicating whether a word can be ADJ, and the subembedding set Z ADJ be responsible for encoding the ADJ. In our algorithm, there is an objective function designed for maximizing mutual information between Z ADJ and A. Meanwhile, mutual information between A and the other subembedding sets will be minimized. The second property of our DWE is compactness. It demands that when encoding an attribute, the number of dimensions of a subembedding set should be as small as possible. In this work, we propose a variational inference method to ensure the compactness property and decide the number of dimensions by learning from data. In fact, each dimension in the DWE has its own score table. The score indicates the relevance between the dimension and corresponding attribute. A higher score means stronger relevance. Therefore, in this example, this dimension will be assigned to ADJ subembeddings. It is also possible that all the inference scores of a dimension are low. In this case, the dimension will be assigned to unseen subembeddings. To decide whether the scores are low, we set a threshold, which is a hyperparameter. If the threshold is high, more dimensions will be classified as unseen. At the same time, other subembeddings thereby become more compact and pure. The third property of our DWE is preserving co-occurrence statistics of words. Ideally, the knowledge implicitly encoded in the original word embeddings can thereby remain after transformation. We achieve this by constraining the matrix for transformation to be orthogonal. Here we provide an example showing that the properties can help us easily obtain the compact and effective features for downstream tasks. In this example, we are solving a document classification problem. Specifically, it is the IMDb sentiment analysis task. We get document embeddings by averaging pre-trained word embeddings, and the classifier is logistic regression. The word embeddings used here is 300-dimensional glove, we transform it by our algorithm and get the DWE, which is also 300-dimensional embeddings. Now, sometimes we may need extremely low-dimensional vectors for training a classifier. A typical example could be a hardware limitation. In this case, we can directly take the relevant sub-embeddings for the task. In sentiment analysis, intuitively, the ADJ and ADV sub-embeddings are more likely to be useful. Therefore, we take these two sub-embedding sets, which have 52 dimensions in total, and compare them with 50-dimensional globe. By experiments, we found the sub-embeddings can achieve better classification accuracy. It implies that high-dimensional embeddings with modular structures could be more favorable than regular low-dimensional embeddings. With disentanglement, we also found polysemous semantics can be easily revealed. Take the word turkey, for example. We found that the nearby words are geese, flock, and goose in the animal sub-embeddings. On the other hand, the nearby words become Greece, Cyprus, and Ankara in location sub-embeddings. Therefore, despite the learning algorithm of globe does not do disambiguation explicitly, the polysemous semantics can still be extracted and clearly presented. Finally, with the property-preserving co-occurrence statistics, the DWE is expected to preserve most information encoded in the original word embeddings. We evaluate this by conducting the following intrinsic and extrinsic evaluation tasks. We found that DWE can show similar or slightly better performance than the original word embeddings on the tasks. In summary, we propose a methodology for introducing disentanglement into typical word embeddings. With disentanglement, the word embeddings can have higher interpretability, easily generate compact and effective features, and not sacrifice performance on general NLP tasks. That is all. Thank you.